is Aaron Potechin, and we will talk pseudo-calibration, sum of squares, and planted Clique.
Okay, thank you for the introduction. So today I'll talk about sum of squares, planted Clique, and pseudo-calibration. So as you may remember, my collaborator Pravesh Kothari talked on Tuesday about the sum of squares hierarchy, which is a powerful tool for combinatorial optimization. In this talk, I'm going to talk about the lower bound side, so how you can show that the sum of squares hierarchy does not work at a given degree. And if you don't remember, that's OK, because I'm going to review the sum of squares hierarchy now. So what the sum of squares hierarchy does is it gives tests for whether a set of equations such as these, polynomial equations, are infeasible over the real numbers. In particular, it determines whether or not there's a degree D positive Stellan-Zotz proof, where degree D positive Stellan-Zotz proof looks like this. So now if such a proof exists, then the equations are infeasible, because this has to be 0 for all I. This is always non-negative over the real numbers, so this can't be equal to -1. Now it turns out by Stengel's positive Stellan-Zotz, if the equations are infeasible, then there will be a positive Stellan-Zotz proof, but the degree could be very high. So now, so the questions which we're investigating are, at what degree will there be a positive Stellan-Zotz / SOS proof of infeasibility? And if there's no such proof, how do we show it? So to show that there is no degree D SOS proof, we look at the dual, which are, it turns out the dual is what is called pseudo-expectation values. So pseudo-expectation values are a map from polynomials to values, or a linear map from polynomials to values. And the idea is that they look like the expected values over a distribution of solutions. So, do the values have to be positive? On squares, they should be. It's just a linear map. I mean, I'm going to say what the tests, what conditions they should satisfy right now. So they should satisfy the following tests. So test 0 is that the pseudo expectation of of 1 should be 1. So the next test is that it should obey the equations we expect it to obey up to degree D. Because this is always true for any actual solution. And then the final test is that for any square, the pseudo expectation value of any square should be non-negative, because for any real solution, all squares are non-negative. What was that?
It's linear also.
And yeah, it's a linear map. That is absolutely correct. So
what do you expect until the FI, SI equals 0?
because the equations we're analyzing are that all the SI are equal to 0. So whatever you multiply them by, it should still be 0.
For x in the x is, you should think of something, a real vector that satisfies all of this equation. We want to prove there are none. No,
Yes.
And so Fi can be anything.
fi can be anything as long as the degree is not too high. Oh, I should say, yeah, this here is for degree d sum of squares, like showing that there's no degree d proof.
B tilde might as well be defined only for polynomials up to the degree.
Yes. All right, any more questions before I continue? Okay. So if E tilde exists, then there does not exist sum of squares proof of infeasibility. And to see this, degree d, to see this, assume there is such a proof and apply these pseudo expectation values. So remember that the proof has the form -1 equals this here. So now if we apply E tilde, this has to be -1. This part here, it has to be 0. And oops. Heck. And this part here is non-negative, so this gives a contradiction. Okay, so to summarize, yeah, by strong duality, it is an if and only if. So, right, one more thing I should say before moving on. So that this condition 2 can be expressed very nicely. In terms of what's called the moment matrix. So the idea there. And the moment matrix is indexed by monomials p and by monomials of degree So the moment matrix is indexed by monomials of degree at most d/2. And the entry in row P and column Q is the pseudo expectation of P times Q. And now, if we're given a function, say Gj, so it'll be a linear combination we can write it as a linear combination of monomials. So we can view it as a vector. And then we have the equation that the pseudo expectation of Gj squared is equal to Gj transpose m Gj when we view it as a vector. And this means that the condition that for all Gj, the pseudo expectation of Gj squared is non-negative. This is precisely the same as the statement that m, can you see there? Not so well. I'll write it down below. It's precisely the same as the statement that m is positive semi-definite, or PSD. Okay, so to summarize, so in order to show that there is no sum of squares proof, there's two parts. We have to find what values of E tilde we should use, and then we have to prove that the corresponding moment matrix is PSD. And in my remaining time, I'll talk about the first part. So I'll talk about the first part, in the context of planted Clique. So in the planted Clique problem, we start with an Erdős-Rényi random graph where each edge is there or not there with probability 1/2. And then we add a clique of size omega by picking omega vertices at random and making them all adjacent to each other. And then the question is, let's say I give you such a graph. Can you find the planted clique?
What is omega?
Omega. So in this case, I planted a 5 clique. Thanks.
No, what's its size? I mean, you can find small
5. Size 5. So anyone see it? Okay, I guess so. Yeah, we'll move it down. Sorry. So here the clique I planted was these vertices here, and you can check that they're all adjacent to each other.
Is the only clique of size 5?
I checked, and I believe it is. Okay. How much time do I have left?
Okay, so I would say about 3 minutes and 23 seconds.
Yikes. All right, I'll describe what I can then. So okay, so now the problem that we actually analyze is can we prove that a random graph has no large clique? So now I believe Pravesh gave these equations Tuesday, but I'll give a refresher. So the equations for whether a graph has a clique of size omega. The idea is that we'll have xi equals 1 if I is in the clique, and 0 otherwise. So first, for all I, we want xi squared to equal xi. This forces all the xi's to be 0 or 1. We want that xi times xj is equal to 0 if I is not adjacent to j. This forces the 1's to be a clique. And finally, we want that the sum over I of xi is equal to omega. This says the clique has size omega. So the graph has an omega clique precisely when these equations are solvable. And so even though what we're actually doing is showing that we can't certify a random graph has no large clique, it is useful to think in terms of comparing the random distribution and the planted distribution. A random and planted distribution. So in the random distribution, we have gn 1/2, and well, yeah, you have to figure out what E tilde to use. In the planted distribution, I should say that in our actual result, we have to weaken this equation a bit to say that we only satisfy it approximately. Intuitively, it shouldn't make a big difference, but at the moment we don't actually have a proof of that. But anyways, it's useful to think in terms of comparing two distributions. We have the random distribution and the planted distribution. where in our planar distribution we place each I in the clique independently with probability omega over n. And then our actual solution, and then we have an actual solution which, so if we define xv for a set of vertices v to be the product of all the elements in v, then we have their actual solution is xv is 1 if v is a subset of the clique, and 0 otherwise. OK, so it looks like I won't have time to get to the actual pseudo-calibration, but I guess let me just say a few final words about getting this e tilde. So the first attempt, which is fairly natural, is to place equal weight on cliques and 0 weight on non-cliques. And as a side note, this is what Avi and Raghu did in their original paper, and what we did in our analysis at first. And it gives non-trivial bounds, but does not give the full bound. So the second step was to try and fix what went wrong in try number 1, but that's kind of ad hoc. And the actual answer for what we should do is pseudo-calibration. And I think I better stop here.